Now let me turn things over to our presenter. Vicki, the floor is yours.
Thank you, Nancy. Hello, everyone. Today we are going to spend the next hour or so discussing how to make ultra-low level current measurements. And hopefully by the end of today's webcast, you'll learn to identify what is the common customer problem out there and how do we solve it. You will also learn some design techniques associated with electrometer circuits. And next, you'll learn measurement challenges, in particular, the physical implementation of the hardware itself. I also like to share with you some tips and considerations based on my own experience of building these low-level current measurement systems. I'd also like to introduce you ADI's ultra-high sensitivity femtoampere measurement platform. And for the last 5 minutes of the webcast, I'd like to talk to you about the photoelectric demo that I've put together that utilizes the femtoampere measurement platform. So first, let us identify what the customer problem is. Well, analog devices, we are very committed to customers' evolving needs and bringing the best solution, especially in the lab and scientific instrumentation market. Well, if you look at the snapshot that I have on the left, this is ADI's Volume 1 analog dialogue publication, and it was published back in June 1967. So that was 50 years ago. So in that article, we talked about using amplifiers for flame detection in gas chromatography application. And throughout the years, we are constantly keeping up with the evolving needs and coming up with better and better solutions. So fast forward to 50 years later, we released an electrometer grade amplifier, and this amplifier has industry's lowest input bias current. Well, it's targeted to multiple high sensitivity applications, and gas chromatography could be one of them. Here are some examples of instrumentation applications like chemical analysis, environmental metrology, or process monitoring. And they use different analytical measurement methods like mass spectrometry or spectroscopy. So remember spectroscopy because we are going to talk about it in more detail later on. And to the right of the slide, these are example systems with the ones that are highlighted in the red box are the ones that we identify as needing ultra-high sensitivity measurements. And with this ultra-high sensitivity equipment, there is a need for high precision, high sensitivity, precision signal chain, and also a need for lower level of signal detection. So let us look at what is the limit of detection out there. Well, take a look at the diagram on the right of the slide. To measure a signal, the measurement level has to be above the noise. And as the need for higher sensitivity equipment increases, there's a need for lower and lower level of signal measurements. And this requires us to go very close to the shaded area. We are very close to the limit of detection. And with these measurements, special and very unique considerations that we otherwise would not think of now has to be taken into account to allow us to achieve really precise and accurate results. And many times for low-level current measurements, electrometers or electrometer circuits or electrometer grade amplifiers, they are often used. So before we move on, I'd like to first define what an electrometer is to make sure all of us are on the same page. So an electrometer is an electrical instrument for measuring electric charge or electrical potential difference with very, very low amount of leakage current. You can use it as a voltmeter, an ammeter, ohmmeter, or a coulometer. And one of the main specs of an electrometer is that it has very, very high input impedance. And when I'm talking about very high input impedance, I'm talking about, say, above 100 tera ohms or as high as 10 peta ohms. And for those of you out there who are not familiar with these SI units, tera refers to 10 to the power of 12 and peta, 10 to the power of 15. So that's really, really high. An electrometer also has very low input offset current. It could be in the femto-M or even atto-M region. And again, femto-M in this case refer to 10 to the power of minus 15 and atto 10 to the power of minus 18, ultra, ultra low. And oftentimes, electrometers also uses transimpedance amplifier for current to voltage conversion in current measurements. So we talk about the need for lower level of detection for increased sensitivity. So here are a couple of high sensitivity detectors that really require precision signal chains. So for example, for current output detectors, there are electron or photon multipliers or even photodiodes. And these sensors outputs a current that needs to be converted into a voltage. So typically the signal conditioning circuit around it would be a transimpedance amplifier. We also have charge output detectors, for example, flame ionization detector or Faraday cups. And these detectors are often used in applications like chemical sensing or like gas chromatography that we talked about earlier. For the next few slides, let's dive into more detail into an application that uses a photodiode as a detector in spectroscopy application. So spectroscopy is the study of interaction between matter and radiated energy. And matter in this case refers to, say, liquids or gases, and radiated energy refers to light. So we use spectroscopy techniques to answer two basic questions about an unknown sample. The first one is, what is it? And the second, how much is actually in there? This is a block diagram of the spectroscopy application. Well, we have a light source. The light source is chopped, and the chopped light source actually gets shone onto an unknown sample. And the unknown sample could either absorb the light or allow the light to pass through. So the light that passes through gets detected by the detector, and in this case, it's the photodiode. The photodiode then outputs a current that gets picked up by a transimpedance amplifier. The transimpedance amplifier converts the current to a voltage. The voltage is then further digitized by an ADC and then further processed. And ultimately, we get an output spectrum. And that output spectrum gives us all the information that is needed to tell us what the unknown sample is. So this is actually the basis for almost all light-based measurements out there, especially in the lab and scientific instrumentation space. And the part of the signal chain that we are going to focus on is what I consider to be the crux or the most important, most critical part of the application, because oftentimes it tells you what the limit of detection is. And what I'm talking about is the sensor and the signal conditioning circuit around it. So this is a close-up diagram of the sensor and the amplifier. Again, the sensor is a photodiode. It converts light to current. And the amplifier converts current to voltage. So let's put some numbers around it. So say we desire an output of 10 volts. We have a full-scale current of 1 nanoamps. And so we choose a feedback resistor of 10 gigaohms. Say our temperature could vary from 15C to 35C. Well, I've put together this table, made some calculations on how using different amplifiers could introduce different amount of output error. And if you're wondering how I came up with these numbers, well, stay tuned because I'll be going through a design example later on that explains how we come up with these numbers. So depending on the application, or let's say your targeted accuracy, or even your budget, any of these amplifiers might fit your need. But remember in this particular example, I'm doing calculation for a full-scale current output of 1 nanoamp. And as we need higher and higher sensitivity equipments, the current that we are sensing is getting smaller and smaller. So essentially, we are reaching the limit of detection. And so the amplifier accuracy and precision that we need gets more and more demanding. So in a lot of system applications out there where they cannot tolerate error, well, definitely an electrometer grade amplifier. In this example, the ADA 4530 would be a perfect fit. So this example illustrates how important it is to have an electrometer amplifier, particularly in a photodiode application for low-level current measurements. Well, here is a cheat sheet for the ADA 4530. I'm not going to go through the numbers, but basically just want to remind you that this is not your typical amplifier. It has really low input bias current. In fact, IB is 0.1 femtoamp typical at 25C, and that is equivalent to 624 electrons per second. Well, IB is also production tested up to 20 femtoamps, over time up to 85C. It's an amplifier that's very easy to use. We have an integrated guard buffer that can be used to drive guard traces that is necessary to isolate input pins from leakage. And lastly, the pinouts are also optimized, and the pinouts is positioned in a way such that the input pins will be isolated from the supplies and the output pins and allow really easy routing of your guard traces. So we look at amplifiers being used in TIA configurations, and we consider that as the core of low-level current measurement design. So I'd like to start by going through a design example around a TIA circuit. So here are some implementation challenges, and these implementation challenges are actually what I personally experienced while trying to put together a low-level current measurement system. Well, the challenges could range from contamination, dielectric absorption, electrostatic coupling, or even error from the amplifier itself. So I'll start by looking at the amplifier first, and then its surrounding components, and understand the design a little bit better. So here's a design example. So again, say we have a photodiode as a detector. This is a large area, high sensitivity photodiode, the Hamamatsu S1226. And the maximum output current is 500 picoamps. Well, we talk about using 4530 for TIA circuit because of its really low input bias current, low offset, low drift. And so naturally the next question that someone would ask is, what kind of transimpedance gain should I use in application like this? Or in short, what value of RF should I use? And before I answer that, let us understand the detector a little bit more. So here is a simplified model of the photodiode. It consists of a current source. It has a shunt capacitance and a shunt resistance. So the shunt capacitance is actually modeling the depletion capacitance of the photodiode, and this depends, say, on the area of the photodiode and also the voltage bias. The shunt resistance represents the voltage versus current slope of the exponential diode curve near the zero bias voltage. And all these numbers are actually available in the data sheet. So as you can see here, C shunt is characterized to be 35 puff, and R shunt 50 gigaohm typical and 5 gigaohm mean. And these are from the Hamamatsu data sheet. So usually in low-level current measurement, we use TIA circuit. And the design goal of a TIA circuit is usually to maximize signal-to-noise ratio and to minimize DC error as well. So one of the ways that we can maximize signal-to-noise ratio is by increasing the value of the feedback resistor. Well, this might sound counterintuitive to you, but let us look at some equations that's going to back up that statement. Well, every resistor has a corresponding noise. That's what we call as thermal noise. And it's a function of square root of 4kTr. In this case, K refers to the Boltzmann constant, and T refers to the temperature, and RF refers to the value of the resistor. The photocurrent from the photodiode flows through the feedback resistor and creates an output voltage. So that is a signal. So from here you can tell that, well, the signal increases as a function of the feedback resistor, and the noise increases as a function of square root of the value of the resistor. So this tells us that the signal-to-noise ratio actually is directly proportional to the square root of RF. So if you want to improve SNR, make RF as large as you possibly can. Well, practically, there's a limit to how large you can make a feedback resistor. Well, you can't make it indefinitely huge, right? So the photocurrent flowing through the feedback resistor would create an output, and the output is going to be limited by your power supplies of the amplifier. So output swing will be something that you want to think about when choosing the value of your feedback resistor. So in summary, in order to improve SNR, you want to use a feedback resistor that is as large as you possibly can within your own design constraints. So next, we're going to look at the DC error budget associated with using the 4530 in a photodiode application. We are going to look at the error at 25C and the error at 60C. So the numbers in green are actually gotten out from data sheets, and the number in blue are my calculation. So first, let us take a look at R shunt. That's a shunt resistance from the photodiode. And at 25C, the data sheet says that R shunt is characterized to be 5 gigaohms. And one thing to note about R shunt is that the resistance actually decreases as temperature increases. And as a rule of thumb, the resistance actually halves with every 10 degrees C increase in temperature. So with this, we calculated the resistance to be 442 megaohms at 60 degrees Celsius. The offset voltage from the data sheet of the amplifier shows 40 microvolts. And the 18 microvolts at 60C is a contribution from offset drift. The noise gain of this whole system is a function of the feedback resistor and the shunt resistor. And again, as I mentioned earlier, the shunt resistor decreases with increasing temperature. And so noise gain increases with increasing temperature. So with information of offset voltage and noise gain, we can then calculate what the offset error is, referred to the output. And I also mentioned that IB, input bias current for the 4530, is production tested up to 20 femtoamp over temperature. So I've put in the worst case spec of 20 femtoamp for IB. And input bias current flows through the feedback resistor, and that gives us 200 microvolt of error at the output. And altogether, this leads to a total error of 32 femtoamp referred to input at 25C and 150 femtoamp at 60C. So now, is the amplifier specifications important? The answer is absolutely yes. And I'm going to illustrate this by making the same calculation with a competitor spot, and then we can have a side-by-side comparison. So this is the calculation for COM-A. I'm not going to go through the calculations again, but what I want to point out is that at 25C, COM-A has 65 femtoamps of error referred to input, and at 60 degrees Celsius, it increases to 900 femtoamp. And this is 6 times greater than what we would have gotten from using the 4530. So yes, if you want to minimize DC error, use a precision amplifier with low offset, low drift, low IB. And the 4530 would be a good part to start off with for ultra-low current measurements. So we talk about DC performance. Let's move on to AC performance. Well, to understand AC performance, we need to look at the TIA noise gain plot. Well, at low frequency, the noise gain at DC is basically a function of RF, the feedback resistance, and R shunt from the photodiode. The feedback resistor would interact with the shunt capacitance of the photodiode, and that creates a 0 in the noise gain plot. So beyond F1, the noise gain is going to continue increasing until it hits the open loop gain plot. And this is a sign of instability. So what you really need is to recover the phase shift by creating a pole in the noise gain plot to stabilize the system. And the way you do it is by introducing a feedback capacitor. So a feedback capacitor together with a feedback resistor adds a pole in noise gain plot and destabilizes the system. And beyond F2, the noise gain is then dominated by the high frequency noise gain, which is a function of the shunt capacitance and the feedback capacitance. The point where the noise gain intersects with the open loop gain tells us what the closed loop bandwidth is. So there are 2 things to note from this slide. First, you'll need a feedback capacitance to stabilize the system. Second, the signal bandwidth is actually very different from the closed loop bandwidth. signal bandwidth is f2 right here, closed loop bandwidth f3. So remember this because we're going to come back to this in our noise calculation. So here are a couple of noise sources that I've identified. I mean, there are a lot more noise sources out there, but for the sake of today's webcast, we're just going to focus on these 4 noise sources, namely the thermal noise of the feedback resistor, the amplifier inherent voltage and current noise, as well as the photodiode noise. So I'm going to look at all this noise as low frequency noise and high frequency noise. And when I talk about low frequency noise, I'm actually referring to noise where the bandwidth is limited to the signal bandwidth f2, and in this case it's calculated to be 50 Hertz. Well, remember earlier I mentioned that signal bandwidth is completely different from closed loop bandwidth. So for low frequency noise, all these noise contributors are limited by the signal bandwidth. So the first noise contributor is from the feedback resistor. We talked about thermal noise of a resistor earlier as being square root of 4 kTr. So the thermal noise of this feedback resistor actually gets reflected directly to the output, but it's limited by the feedback capacitor. And so the bandwidth is limited by the signal bandwidth. Well, the second noise contributor will be from the photodiode. And the noise of a photodiode, we can model it as the thermal noise of a physical resistor with the value of R shunt. And in this case, the thermal noise is going to be amplified before it gets to the output. And it is going to be amplified by the ratio of the feedback resistor to the shunt resistor. And again, this is going to be limited by the signal bandwidth. The third noise source will be from the amplifier itself, its inherent current noise. Current noise is going to flow through the feedback resistor and creates a voltage noise at the output. So this gives us a total referred to output noise of 195 microvolt RMS at 25C and 585 microvolt RMS at 60C. So the noise is actually much higher at higher temperature because of a couple of reasons. Well, first, we know that thermal noise increases with square root of the temperature. And second, we also know that the shunt resistance reduces with higher temperature, which means that at higher temperature, your noise gain would increase, causing a higher noise at the output. And third, the amplifier current noise also increases as temperature increases. Next, let us take a look at the high frequency noise. And you will see that the high frequency noise is largely dominated by the amplifier voltage noise. In this case, the voltage noise is going to be gained out by the high frequency noise gain, and it's a function of C shunt over CF. And in this case, the high frequency noise is going to be limited by the closed loop bandwidth of the system. It is really much higher at 17 kilohertz. And this gives us a total of 271 microvolt RMS at 25C and 286 microvolt RMS at 60C. So noise due to voltage noise density of the amplifier is significant due to 2 reasons. First, noise gain is higher due to the ratio of C shunt over CF. And second, noise bandwidth for the voltage noise of the amplifier is much, much higher compared to the noise bandwidth of the other noise contributors. So here's a summary of that low frequency as well as high frequency noise. And a few things to note with this noise exercise. Well, actually 3 things I could think of. Well, first, different noise sources, well, they have different noise bandwidth associated with them. Second, at low temperature, the amplifier voltage noise is more significant compared to any of the other noise sources. And third, majority of this voltage noise actually happens outside the signal bandwidth of the circuit. Remember, the signal bandwidth is only 50 Hertz. So this tells us something. It tells us that we could probably mitigate the noise contribution from voltage noise of the amplifier by limiting its bandwidth. And the way we can do this is by placing a simple low-pass filter after the TIA circuit. So here's a slide that summarizes the total noise and its associated SNR. So without any low-pass filter, total noise is about 333 microvolt RMS, and SNR is 89.5 dB. With the addition of the post low pass filter, and say we choose an RC network with a cutoff frequency of 500 Hz, it brings the high frequency noise down by a factor of 6 and essentially boosts up the SNR to 94 dB. So this is actually a neat trick that you can perform in your next design to minimize noise and to maximize SNR in your TIA circuits. So we spent a long time looking at design techniques. Well, next, let's look at measurement challenges. And I think most of us will probably face these challenges when we are trying to implement ultra-low level current design. And a lot of these are challenges that I actually experienced. And so I thought it would be nice to share my experience and learnings with you. So here, well, when doing ultra-low level current measurement, I guess the number one fear would be leakage. So I recommend doing guarding. And guarding is actually a technique to surround the insulation of your high impedance node with another conductor that is driven to the guard voltage. So the guard voltage is going to be at or very close to the high impedance node potential. So if you look at this picture here, well, you have a signal trace and it's completely surrounded by the guard. And let's just say that the guard potential is the same as the signal trace. And there is no potential difference across the insulation resistance then. I mean, the insulation resistance is between the signal trace and the guard. So if there's no voltage potential difference, there cannot be a current flow. And if there is a potential leakage, then majority, if not all of the leakage, will actually happen between the guard trace and the other leakage node. So this way, the signal trace actually maintains its signal with no leakage. Well, in practice, it is actually not possible to completely surround the high impedance node. But there are a couple of structures that we can implement in terms of layout techniques that can yield better performance. So here are a couple of guarding structures that you could implement. The first is guard rings. Well, if you are familiar with low-level current measurement, most likely you are familiar with guard rings as well. Well, guard rings, they guard surface leakage. If you look at the photo on the right, the guard ring is that filled copper-shaped surrounding pin number 1, which is the high impedance node. And we would suggest you to remove solder mask and silk screen on your guard rings and traces, because these ensure that the guard traces make electrical contact with any surface leakage path. And also we want to avoid moisture absorption by the solder mask or the silk screen. And one of the difficulties of implementing guard traces is that you might actually need an external amplifier to drive the guard traces. Well, the good news is, with the 4530, it has an integrated guard buffer, so that simplifies the design, and you can use the internal guard buffer to actually drive your guard rings or guard traces. The other technique that I would apply is to implement a guard plane. So the structure of the guard plane is shown in the cross-section of the PCB here. It's the filled copper shape placed directly below the high impedance trace, in this case labeled as A. Well, the guard plane is connected to the guard traces on the surface using vias. And in hybrid stack-up dielectric material on your board, and probably that's what you would have for low-level current measurement. And in this example, the outside layers are Rogers 4350B material. The core layers are conventional FR4. Well, it is very important to place the guard plane on the boundary of the ceramic Rogers material and the glass epoxy FR4 to protect the high impedance node from the poor dielectric absorption characteristics of the glass epoxy material. So place it at the boundary of the Rogers and FR4 material. And the last structure that I think is very effective as well is a via fence. So via fence basically got lateral leakage path, and you can implement it by surrounding the guard ring with vias. So if you look at the diagram on the bottom right of the slide, the little dots, these are vias, and they actually surround the guard ring, and they connect the guard ring to the guard plane underneath the high impedance trace. So these are a couple of structures that you could implement on a PCB design to reduce leakage. Next, I'd like to spend some time talking about contamination because this is one of the major challenges that I actually faced when I was doing low-level current measurement. So here are a couple of contamination sources. For example, solder flux residue, dust, dirt, or even body oils. And all these contaminants is a big issue for low current measurement system. So what we did was an experiment in lab. Well, we had a PCB insulation with 2 high impedance nodes, and it was purposefully contaminated by RMA solder flux. We then allow it to dry in lab condition, and say a few days later, we measure what the current to voltage response is, obviously with an electrometer grade SMU. And what we realized is that the contaminant actually acts like an electrolyte. It formed a weak battery, and the open circuit voltage is measured to be about 15 millivolts, and output resistance to be about 300 gigaohms. So the figure on the right shows a simplified model of how the voltage and the resistance would corrupt our measurement. So say for example, when node A and node B, when they are both driven to the same potential, and that's usually the case in a TIA configuration, an error current, which is equivalent to VBAT over RBAT, is then created, and this error current flows through the feedback resistor, creating an error at the output. So in this example, the error current actually came up to be 50 femtoamps. Well, it's really low, 50 femtoamps, and might not be a big deal for typical applications. But for a very low-level current measurement, using an electrometer grade amplifier, this error current would totally swamp your measurement. And this type of contamination is really bad because guarding technique cannot suppress it efficiently, and the best way to deal with it is by properly cleaning your board. So we suggest washing and cleaning your board after assembly. And if your board is really contaminated, what we found out is ultrasonic cleaners that are pretty effective because they create ultrasonic high frequency, and this creates cavitation that could remove contaminants from hard to reach area under solder mount components on your board. So definitely probably check out ultrasonic cleaners if you have problems with contaminants. Well, moisture will definitely get into the board as well. It could either adhere to the surface of the board or enter through bulk of the material. So you want to choose appropriate material that reduces problem with moisture. So the table on the right shows a comparison between 2 different materials and their associated moisture absorption. And obviously from the table, it shows that PTFE material would be more recommended to be used because of its better moisture absorption performance. Well, after you wash your board, you can also leave it out to completely dry in room temp, but it's going to take a very long time. It's going to take, say, hours, if not days. So we do recommend baking a board after washing to drive out moisture from the board. And one thing I really want to point out in this webcast is that never ever use no clean solder paste. Well, we have been bitten by that, and I actually did an experiment in lab where I find out what is the different cleaning procedures for different solder paste material. So long story short, the no clean solder paste, well, you actually still have to clean the board, and it takes a very long time to clean it and to bake it for us to reach our performance target. So if you want to find out more about an effective cleaning procedure, check out UG 865. It illustrates a step-by-step cleaning procedure. And again, I can't stress enough, do not use no clean solder paste. Next, dielectric absorption could be an issue too for electrometer circuits. You would probably know these as dielectric relaxation or soakage, and it's the delay in polarization of dielectric molecules in response to an E-field. You would commonly observe it in capacitors or multi-layer PCBs. And you often model it as an RC in parallel with an ideal capacitor. And in electrometer circuits that need to settle, let's say to a few femtoamps, dielectric absorption could be a limiting factor. While small displacement current could flow through the insulator in response to polarization of these molecules. And delay in the polarization actually cause delay in dissipation of the displacement current, and this dominates settling time in the electrometer circuits. So again, we did an experiment in lab comparing two different dielectric materials, glass epoxy, FR4, and also Rogers 4350. So what we found out is that for glass epoxy, it takes about an hour or so to completely dissipate the current to be less than 10 femtoamps, whereas for Rogers material, it only takes about 20 seconds to dissipate current down to about 2 femtoamps. So from this experiment, I highly suggest you to consider using Rogers material. In particular, we use the 4350B, or you can choose to use PTFE material as well. Well, we have commonly seen customers using PTFE standoff, or what we know as Teflon standoff, for the same reason, to deal with dielectric absorption of the PCB material. So shielding is another thing we need to look out for. While high impedance electrometer circuits, they are very susceptible to interference through capacitive coupling. So you can think of shielding or the shield as being a piece of conductive material that you place between the high impedance node and the interference source. So the shield would basically act as a physical barrier, and it interrupts the capacitive coupling path. So then the displacement current from the interference source is shunted to the shield. And many times the shield are electrically connected to a low impedance source, let's say ground. And this is actually good and safe, especially if you're exposing the shield to operators. So here are a couple of photos that show us implementing shielding on our evaluation boards. So the evaluation board at the bottom even shows shielding on the top of the PCB as well as at the bottom of the PCB. So we talk about guarding on a PCB level, while guarding on cables and connectors are also equally important. So I suggest you to try out Tri-X connector. While Tri-X connector, it has an extra inner conductor to guard the signal. And basically, it's the same concept as guarding, like what I mentioned earlier. The guard conductor will completely surround the inner conductor that is connected to the high impedance terminal. And since there's no potential difference between the guard and the signal, there's not going to be any leakage current. And the shield, which is the outer conductor, is then connected to the low impedance terminal. And if you only have coax cable like BNC and SMA, it is okay as well, as long as there is very little potential difference between the center conductor and the shield. So for a coax cable, the inner conductor is typically connected to the high impedance terminal, and the outer connector is connected to the low impedance terminal. So this is perfectly fine, especially in TIA interface circuits, because it effectively guards the insulation resistance between the inner and the outer conductor. So then there's no potential difference across the insulation resistance, and so again, no leakage current. We also suggest tying down cables to reduce triboelectric effects. So for example, you might have cables and you might be flexing it, or you might be moving cables across your table, and that could generate charges. So triboelectric effects is generation of electric charges due to friction of dissimilar material. So tying down the cable will definitely help reduce triboelectric effects. So here is a summary of the different challenges that we have, the source of the challenge, and some solutions. So the good thing about this is, well, ADI actually provides a femtoampere module that solves the problem. What uses the appropriate guarding techniques, board material, and so on, and it takes away your pain of needing to figure all the challenges out and to implement the solution. So this allows you to do really quick prototyping, and I'm really excited to bring to you our femtoampere measurement platform. So this is a development module for sensors with really low level current output. It allows direct interface to sensors like photodiodes, Faraday cups. Well, it has very high sensitivity of less than 10 femtoamps. And we also populated a 10 gigaohm hermetically sealed glass transistor on the board. And it has a bunch of components in it. Like it has obviously the femtoampere op-amp. It has a 24-bit ADC. It has isolators in it. It has regulators, references. And it only requires a 9-volt DC supply. And we also provide a USB interface to PC via our SDP platform. So let's look at the board in more detail. Well, the board actually implements all the solutions to the measurement challenges that I described earlier. Well, the board consists of a mezzanine board, and this mezzanine board is where the transimpedance amplifier resides. And it is also made of Rogers 4350B material for low moisture absorption, low dielectric absorption reasons that I talked about earlier. The mezzanine board sits on top of the data acquisition board. And on the data acquisition board, we have the other components like the ADC, the isolators, the regulators, and the reference, and so on. So the very good thing about this board is that it allows you to directly connect the board to your sensor in your own application environment. So it's really designed for real-world application. So we are very big with documentation. So what we did is we actually documented this whole measurement platform. We described it in detail in our circuit note, and it's CN0407. And we even provided measurement results on the circuit note, so be sure to check it out after the webcast today. And with the board, we also provide an evaluation software. So it allows you to just grab a hold of the board, connect it to your sensor, and instantly read current measurement out of the evaluation software. So it really makes life much easier for you when you want to try to do a designing for low-level current measurements. So next, I promise we are going to talk about photoelectric effect demo that I put together, and this utilizes the femtoammeter module that I was talking about earlier. And before we dive into the demo, let's first understand what does photoelectric effect actually mean. Well, photoelectric effect is the emission of electrons when light is shone onto a photoemissive material. And we know that light has energy associated with it. It's a function of the frequency or the wavelength of the light, and it's also proportional to the Planck constant. It's a universal constant, and we label it as H here. Well, the photoemissive material also has a work function associated with it, and the work function is the minimum energy required to actually eject the electron from the surface of the material. The kinetic energy of the electrons is a function of the difference between the energy of the light and the work function of the material. So remember this equation because we are going to come back to it later when we describe or when we talk about the demo. Also for this demo, we are using a phototube as a sensor. A phototube is a vacuum tube with an anode and a cathode. And the photocathode is actually made of an alloy of cesium and antimony. So the main objective of this demo is for us to find out what is the work function of the phototube, or what is the work function of the photocathode that is made out of cesium antimony. So here is a block diagram of our demo. Well, we have a light source, and the light source is shone onto the phototube, which is our detector. And this allows electrons to be ejected from the cathode, and it gets swept across the anode. And this creates a photocurrent. The photocurrent is going to be detected and measured by our femtoammeter module. And what we do next is we actually apply a voltage to oppose the electron flow from the cathode to the anode. And this is what we call as the stopping potential, and it allows us to measure what the kinetic energy of the electron is. And with information of the energy of the light, which is from the wavelength and from the frequency of the light, as well as what Planck constant is, and with information on the stopping potential, we can then use the equation that we talked about earlier to measure and to calculate what the work function of cesium antimony is. So here are our measurement results. And as expected, the stopping potential actually varies with light frequency. So as light frequency increases, it has more energy. And when you have more energy, you actually need more stopping potential to stop the electron flow from the cathode to the anode. And from this demo, we measured the work function to be about 1.86 eV. And this demo is actually very analogous to what customers are doing out there. So they have an unknown sample, and they are using electrometer circuits to determine what the unknown sample is. And in our case, the unknown is the work function of the photocathode or the work function of cesium antimony. So this demo allows us to determine what the unknown work function is, and it is done with the femtometer measurement platform to essentially measure up to 0 electrons being swept from the cathode to anode. And we don't really need any expensive or sophisticated electrometers for this. Just an photoampere module would do. And here are some takeaways from this webcast. I hope you learned something. So it is important to minimize output error and maximize signal-to-noise ratio to achieve high sensitivity current measurements. Well, we know that minimizing output error demands a high-frequency amplifier with really low IB, low offset, and low drift. We know that maximizing SNR requires careful selection of gain component. Design of low-level current measurement hardware also requires detailed attention to unique considerations that we otherwise might not even consider. And board leakage, contamination, moisture, and so on can contribute to significant measurement errors. And we also provided some best practices such as guarding, shielding, and cleaning, and so on that could mitigate the error. And the good news is ADI actually provides that high sensitivity femtoampere measurement platform. It provides you the out-of-box experience of being able to directly connect the board to your sensor in your own application environment. So lastly, here are some useful links. Be sure to check them out if you want to find out more about low-level current measurements. And thank you very much for watching. I hope you learned something from today's webcast that you can use and implement towards your next design. Thank you.
Okay, Vicky, our first question is, how many electrons can you count with this reference design?
That's a very good question. I guess it pertains directly to the title of the webcast of counting electrons. So the core of this reference design is the electrometer grade amplifier. So I mentioned earlier about the spectacular input bias current specifications of the ADA 4530. Well, it's actually production tested up to 20 femtoamp and over temperature. And that's also because of measurement limitation of the production environment rather than the part itself. So the sensitivity of the reference design board actually depends on a couple of things, like the amplifier or the size of the resistor that you eventually end up using, and say the sampling rate of choice. So, well, in lab, we actually measured the noise of the entire board to be about 1 to 2 femtoamp RMS with the default 10 gigaohm glass encapsulated resistor and with the lowest sampling rate of 0.83 sample per second. So if you really want me to put it in terms of electrons, well, this would probably be equivalent to 10,000 plus electrons or so per second. And obviously for higher sampling rate, I mean, the noise would be slightly higher and the sensitivity of the board would decrease, but it should still be less than 10 femtoamps or so.
Wonderful, thank you. Okay, our next question is, do I need to worry about environmental considerations like humidity with this design?
Well, I guess humidity is something that I didn't really have a chance to talk about in this webcast. But short answer, yes. For ultra high sensitivity, low level current measurement, well, every little thing could contribute to leakage and they have to be considered. All electrometer circuits, they are subject to humidity effects. This is very true, especially at low temperature. Well, the insulation resistance of the circuit material, they can absorb moisture. So moisture can either adhere to the surface of the circuit material or it could enter the bulk of the material. So at low temp, the insulation resistor could actually create more leakage current error compared to the amplifier itself. So while actually characterizing the amplifier's current sensitivity to relative humidity, what we learn is that the magnitude of leakage current actually changes by, I say, a factor of 100 or more when we sweep relative humidity from, say, 5% to 80%. Well, the effective current is still about probably 1 to 2 femto-amp typical for a controlled environment of, say, less than 40 to 50% relative humidity. But the effective current becomes really sensitive at high humidity levels. Well, if you use legacy amplifiers that have considerably larger input bias current, well, it might be okay because IB would essentially mask the humidity effect. But for amplifiers like the 4530, for electrometer grade amplifiers in general, well, extra caution has to be taken. So for example, you can use it in a control environment. You make sure that humidity level is less than, say, 50%. Or say use Rogers dielectric material because we know that conventional glass epoxy FR4, they have poor humidity absorption properties. Well, we could also say reduce humidity fluctuations with an air baffle, like using a shield. Or even when handling the board, I mean, this is going to sound funny, but you want to be careful not to breathe on the high impedance circuit because that's going to introduce moisture and that's going to corrupt your measurements. So yes, definitely when you're dealing with electrometer circuits, you really have to worry about every little things, and humidity is one of them.
Those are some really great points. Thank you. Okay, the next question, and looks like our last for today, is how does the AGA 4530 amplifier compare to other electrometer op-amps?
Well, definitely the 4530, it's the market leader. It probably, well, it is the first amplifier that has an integrated guard ring driver. It simplifies the design, and it eliminates the need for you to go source that external driver to drive the guard traces. And its pinouts are optimized. Well, it's positioned in a way that you could isolate the input pins from the supply pins and the output pins, and it allows very easy routing of your guard traces. And in terms of specifications, it has about 10 times better precision compared to the next leading competitor part. It has really low offset and low drift. And I think I've mentioned time and again that the 4530 has industry's lowest input bias current over temperature, and I think over temperature is the key. It has really low IB over temp that allow you to do really low level current measurements. So definitely 4530, it's the market leader in electrometer grade amplifiers.
Excellent. Vicki, I want to thank you again for sharing your extensive knowledge and expertise with us. It's really been great today. Folks, this concludes today's presentation. On behalf of Electronic Design, I'd like to thank Analog Devices and Mauser for sponsoring today's event, and of course, all of you for joining. Have a great day.